Happy Thursday. Been dreary all week, hasn't it? Kind of tough to be in a good mood, but we're doing math, so it's going to cheer up our mood. We left off Tuesday. We were looking at partial derivatives, right? We looked at Laplace's equation. We're asked to determine if three given functions were solutions. We got through the first one. All right, so now we're going to look at the second and the third. Second function, half e to the x plus y. All right, remember, to be a solution to the partial differential equation, it has to satisfy the equation when plugged in. Okay. Start with z sub x. Right, half e to the x plus y, that derivative with respect to x. Be half e to the x plus y, right? With respect to x again, just the same thing. With respect to y, half e to the x plus y, right? And then with respect to y again, just a half e to the x plus y. Right, so if you plug it into Laplace's, or at least the left-hand side of Laplace's, you're going to get e to the x plus y, which is not 0. In fact, that'll never be 0. That's not a solution. Right, it'd have to be 0 to be a solution. X squared minus y squared. What's the partial with respect to x? What's the second partial with respect to x? Partial with respect to y. 2y. Second partial with respect to y. Their sum will always be 0. So x squared minus y squared is a solution of Laplace's equation. In general, right, partial differential equations, solutions are not unique. You can have multiple solutions. I believe the same is true of ordinary differential equations. And generally speaking, you can have non-unique solutions. Questions on taking partial derivatives? Bless you. All right, so turn it in. Moving on. Differentiability, tangent planes, chain rules. Differentiability is only going to be used in theory. So just view the video that's posted on MyOpenMath on what it means for a multivariate function to be differentiable at a point. Then there are the chain rules for multivariate partial derivatives. For the most part, if we're actually calculating a partial derivative, the chain rule, the multivariate chain rules, kind of pointless. Right. They're used if you have, like, let's say a function f of xy, where both x and y are functions of t. Right, then the multivariate chain rule would come into play there. That would be partial f partial x times dx dt plus partial f partial y times dy dt to find df dt. Well, why wouldn't you just plug in what x and y are in terms of t into f of xy, have a function f of t, and then just differentiate it that way? Right? I mean, that seems simpler. So for the most part, I will not be using chain rules if we're actually calculating derivatives. It is good for theory. Right, and I think I have a couple theoretical questions in this problem set where we'll be using the chain rules. What the multivariate chain rules do allow us to do is do implicit differentiation much simpler. Do I have any? I do. Perfect. Right, so we'll be doing some implicit differentiation as well. Makes it a lot easier. Even the Calc 1 implicit is now a lot easier with partial derivatives. So no more of that BS of differentiating the whole thing and then solving for dy dt algebraically, and then it just looks hideous. Yeah, nope, we're going to be doing it much simpler. It's usually about one line of work. Obviously, tangent plane to a surface, right? It's the analog of the tangent line to a curve. Right? It's a plane that intersects the surface at that point. That's a tangent plane, right? So we'll be looking at that. We're also going to look at what's known as the total differential. Right, so remember you had the differential for y in Calc 1, right? If you had y equals f of x, the differential for y dy was f prime of x dx. Right, it's very similar. You have a multivariate function, let's say y equals some function of n variables, x1 through xn. Then your differential for y would be the partial of f with respect to x1 times dx1 plus the partial of f with respect to x2 times dx2, right? So on and so forth. So you just take the partial of each with respect to each independent variable and multiply by the differential for that independent variable, sum them all up. That's your differential. That's your total differential. Much like in Calc 1, the differential can be used for approximations. It can be used to approximate how the function changes if any combination of the independent variables change. We don't really spend too much time on that because sadly I don't have enough time in the semester to do those types of numerical things. But if you're interested, I believe it is in your textbook, so you can read up on that, on how you can use it to do numerical approximations. So go ahead and find the total differential for this function. So we're given z is a function of two independent variables. Differential for z. Since it's addition, the order in which you do the independent variables doesn't matter, right? So we could do the partial with respect to x first or partial with respect to y first. Doesn't matter. I'm going to do x first because, that's kind of standard. So we take the partial of this with respect to x. I'm going to actually write it out. Right, then it's multiplied by the differential for x. And then we'll add it to the partial with respect to y times dy. What is the partial of z with respect to x? And that gets multiplied all by dx. What is the partial now with respect to y? And then that gets multiplied by dy, and there's your differential for z. All right, so again, a natural extension of a topic studied in Calc 1. We again have two independent variables. All right, so we're just going to have two terms in the total differential. Partial with respect to x. Well, I know who's going to answer this, since he just walked in. What's the partial with respect to x of z?
3.
Oh dear, we're in trouble. At least you could have said it was pi.
Then would be contemplated. It would be negative y cosine 1.
1?
Oh no, then you would. Is this where you do the shading?
We actually don't need the chain rule here.
Yes.
What's the derivative sign of x? I'm the one who gives the tests in this room. Congratulations, Carlo's now off the hook. He's not losing 10 points for not bringing me food. You're going to take that heat now.
Take it.
Lucked out. Then we have to do partial with respect to y. Which is what? There's your differential. Yeah. And ignore the fact that I don't know how to spell. Just fixed it. We're given a differentiable function f of x, y, z. We want to evaluate the spherical partials. Right, so we want partial with respect to rho, partial with respect to theta, and partial with respect to phi. This means we need to write x, y, and z as functions of rho, theta, and phi. What is x in spherical? Not just cosine theta. There's still something missing.
Theta sine phi.
What is y?
Theta.
What about z? That's for cylindrical.
Sine. Phi.
Rho cosine of phi. So the partial of f with respect to rho, by the chain rule, partial of f with respect to x times the partial of x with respect to rho plus the partial of f with respect to y times the partial of y with respect to rho plus the partial of f with respect to z times the partial of z with respect to rho. Partial of x with respect to rho is what? Right, since f is just some arbitrary function of x, y, and z, it's just f sub x. What about partial of y with respect to rho? and partial of z with respect to rho. There's partial of f with respect to rho. Partial now with respect to theta. Well, it's going to be the same, except you replace the partial with respect to rho with partial with respect to theta above. What is the partial of x with respect to theta? Be negative rho.
Yes. Same.
Phi. He said negative phi.
Yeah.
If the Greek were still around, they'd be, or the ancient Greeks were still around, they'd be very upset with you. I think they believed in sacrifices, so you might be up on that altar. Just don't know which god they'd be sacrificing you to. God of knowledge, maybe? What's the god of knowledge in Greek mythology? Was it Athena? Wow, it is Athena. Cool. I didn't know Athena was the goddess of knowledge. Guess I didn't pay close enough attention to the Kratos story. Partial of y with respect to theta. Partial of z with respect to theta. There's partial f with respect to theta. And so again, chain rule, we're looking for partial of f with respect to phi. It's just fx times x phi plus fy times y phi plus fz times z phi. What is the partial of x with respect to phi?
rho cosine theta cosine phi.
What about y? And what about z? Oops. Oops. Lovely.
Rho, negative rho sine theta sine phi.
Where?
The dot, middle.
This one? Why would it be negative? Is it? Oh, lovely. Now my mouse is acting up. So these would be if you're given a function in rectangular and asked to find the spherical partials. There's your formula. Or there's your formulas. There's only one additional thing you would need to do. Right? If you take the partial with respect to x, your function, the partial is going to be a function of x, y, and z. You just have to convert that to spherical. Right? So you have to plug in x rho cosine theta sine phi, y as rho sine theta sine phi, and then z as rho cosine phi, right? So you have complete functions of rho theta phi. Right, which is what we're going to do here. Here we're given a function u of x, y, and z, and we're asked to find the three spherical partials. So what's UX? What about U sub Y? And finally, U Z. So starting with U sub rho, it would be what? UX times cosine theta sine phi, right? Plus U sub Y times sine theta sine phi, plus U sub Z cosine phi. But we can't leave it like that, right? That's a mixture of rectangular and spherical. We want it to be strictly spherical. X is rho cosine theta sine phi, right? The first term will become 2 rho cosine squared theta sine squared phi. Y is rho sine theta sine phi. So that second term will become 4 rho sine squared theta sine squared phi. Z is rho cosine phi. So that last term will just become 4 rho cosine squared phi. I don't think that can be simplified. All because of that bloody 2 instead of a 4. Yeah, I don't think that can be simplified at all. I mean, I could write cosine squared as what, 1 minus 2 sine squared? But that doesn't really get rid of a term. Right, that would then allow me to simplify. Oh no, it wouldn't even simplify those middle terms. I need a cosine squared. So if I wrote cosine squared as, what was it, 2 cosine squared minus 1, I could. Right, this is 4 rho sine squared phi, but then I'd still have an additional term. So yeah, there's really no simplification to be made here. Bummer. partial with respect to theta would be negative u sub x sine of theta sine of phi. Plus, why did I not write a negative when I specifically said negative? U sub y. And that was cosine theta sine phi. And then there was no z term. Right, x is rho cosine theta sine phi. Plug that in. Y is rho sine theta sine phi. Plug that in. Oh, look, that can be simplified. So that becomes, wait a minute. Okay, I'm now testing you. Why? Right. There should be rows, right? And it should be ux rho or negative ux rho sine theta sine phi, and then plus uy rho cosine theta sine phi. That can actually be simplified even further. Now I'm testing your knowledge of trig. Because it's negative 2 plus 4, right? Which is positive 2. And that works because, of course, they're the exact same terms, right? We don't remember our trig identities. This is very sad.
Um, like 2 cosine theta sine theta was just simplified as sine 2 theta.
Now, be honest, did you look it up?
I like remember there was like a divide.
I'll give you credit for remembering it's a double angle. Yeah, sine of 2 theta is 2 sine theta cosine theta. We have a 2 sine theta cosine theta, so just replace it. There is another identity we could use. It just isn't going to be a simplification. We could use the sine product to sum formula to rewrite sine of 2 theta times sine of phi. But that would add an additional term, which isn't simplifying. So just leave it like that. Again, you could also do sine squared is 1 minus cosine squared, but that again adds a term. So I'd say that is fully simplified. Now we need U sub phi. U sub x times rho cosine theta cosine phi plus U sub y times rho sine theta cosine phi plus, actually it's minus, right? U sub z rho sine of phi. Then replace x with rho cosine theta sine phi, y with rho sine theta sine phi, and z with rho cosine phi. This can be simplified. It was a simplification we just did.
Just to double it.
All three, don't they have two cosine phi sine phi? There is something else we can do. I don't know if it's really simplifying. Then we're left with cosine squared theta plus 2 sine squared theta minus 2. That can still be simplified. I'm glad I did that because I wouldn't have seen it without doing that.
Cosine squared and sine squared into 1.
You can't in this case because the sine squared is being multiplied by 2 and the cosine squared isn't. So you're saying write 2 sine squared as sine squared plus sine squared? Yes, you can do that. Right, then you'd have what? You'd have a sine squared minus 1, which could be simplified further. Right, so here's what I saw. So yes, that would be valid. Here's what I saw. 2 sine squared minus 2 is negative 2 cosine squared. Right? Cosine squared is 1 minus sine squared. So that would mean sine squared minus 1 is negative cosine squared. Have I ever mentioned how much I love trig? Right. If I really wanted to, I could try and rewrite cosine squared, but no matter how I decide to do it, I'm gonna get an extra term out of it, which isn't simpler than what we have. So I'm just gonna say, there we go. Negative rho squared cosine squared theta sine of 2 phi.
Did it accept it, or do we have to get it as?
I mean, on my open math, it should accept this unless it specifically says to fully simplify.
That's two questions.
Yeah, unless I say specifically to fully simplify, I'd be fine with, any of them. Just be advised that if you try to simplify and you make a mistake somewhere along the way, you are going to lose points for that. Even if you got it correct before simplifying. But if you want to impress me with your knowledge of trig, then fully simplifying would impress me. especially since I love trig.
You should go back up a little. Please.
You didn't tell me how much was a little.
Good. Thank you.
If I could, I would have done 1 millimeter. So here we're going to look at an application of the chain rule. Notice that we're given an implicitly defined multivariate function. Well, in Calc 1, you would have used implicit differentiation, right? For partial z, partial x, we would have just said, okay, we'll take the partial of the entire equation with respect to x, and then solve for partial z, partial x algebraically. And then the same thing for partial z, partial y. But we have chain rules. Let me just double check that I got that order right. I'm pretty sure it is. Oh, wait, what am I doing? I just on here. Yep. And by the way, you can also use this for Calc 1. Write your implicitly defined function y in terms of x as some function f of x, y equal to 0. Then dy dx would be negative f sub x over f sub y. Without the need of having to do all that algebra. So what would our function big F be for this problem? And we want to write it as f equal to 0. So what is f? There's f. What we're gonna need to calculate is f sub x, f sub y, and f sub z. But sadly, we are out of time. So we will pick up here tomorrow.